Hello everyone, welcome to Kanitha Maths channel. In today's video, we will be discussing CBSE Class 12 Maths Chapter 1 Exercise 1.1. Question number 1. Determine whether each of the following relations are reflexive, symmetric and transitive. We have to verify whether the following relations satisfy the above mentioned properties. Number 1. Relation R in the set A equal to 1, 2, 3, etc. 13, 14 defined as R equal to set of all ordered pairs x, y such that 3x minus y equal to 0. So the given set consists of natural numbers from 1 to 14 and the relation defined such that only ordered pairs satisfying the condition 3x minus y equal to 0 will be included in the set R. So now we have to verify whether this relation defined on this set satisfies the above mentioned properties. Our given set consists of natural numbers from 1 to 14 and the relation R is defined such that only the ordered pairs satisfying the condition 3x minus y equal to 0 will be included in this set R. This can be rewritten as 3x equal to y. So now let us write the elements in this relation R. 1, 3, 2, 6, 3, 9 and 4, 12. So only these four ordered pairs will be there in the set R since they satisfy the condition 3x equal to y. We can now verify the three properties reflexive, symmetric and transitive based on this relation. Number 1. Reflexive. A relation is said to be reflexive if for every element in the set A, the element should be related to itself. So if you take an element say 1, it should be related to itself. So 1, 1 should be there. But here we don't have such elements. 1, 1 or 2, 2 or 3, 3 is not there. So in general, x, x is not there in the set R where x belongs to the set A. Therefore, we can conclude that the relation R is not reflexive. In general, we can also prove this without identifying the elements in this relation in the following way. You can randomly pick an element from the set A. So let x belongs to capital A. Now we have to verify whether this element x is related to itself. If an element is related to itself, then it should satisfy the condition 3x minus y equal to 0. So the element x should satisfy the condition 3x minus x equal to 0. But 3x minus x equal to 2x. Since x belongs to the set A where the elements are from 1 to 14, 2x will never be equal to 0. If the product of two elements equal to 0, then any one should be equal to 0. 2 is not equal to 0, then at least x should be equal to 0. But x can never be 0. Therefore, what we could conclude is x is not related to x. So this implies the relation R is not reflexive. Fine. Moving on to the second property, symmetric. A relation is said to be symmetric if A related to B, then B must be related to A. So if you take a pair from this relation, say 1, 3, then 3, 1 should be there. But we don't have 3, 1. Similarly, for 2, 6, we don't have 6, 2. Thus, what we could conclude is for the elements in the set R, we don't have the elements such that A related to B implies B related to A. Therefore, this relation R is not symmetric. So, we can also prove this in the general way. So, let x and y be two elements in the set A such that x is related to y, which means 3x minus y equal to 0. From this, what we have to prove is y is related to x. we have to verify that. So in order to prove that y is related to x, we have to verify whether 3y minus x equal to 0. But from the above condition, what we know is y equal to 3x. So if you substitute this y value here, you will get 9x minus x, which is equal to 8x. Since x belongs to a, this value can never be 0. So this 3y minus x will not equal to 0. So this implies y is not related to x. Though x is related to y, y is not related to x. Therefore, the relation R is not symmetric. Third one, transitive. So a relation is said to be transitive if we take three elements, say x, y, z, and with the condition x related to y and y related to z, then we should get x related to z. Then we can say the relation to be transitive. So in our case, if you take two elements such that x related to y and y related to z, then we have to prove x related to z. For example, if you take 1, 3, where 1 is related to 3, and 3, 9, where 3 is related to 9, but we don't have the element 1, 9. That is, x related to z is not there. So from this, what we could conclude is the relation R is not transitive. So we can prove this in the general way. Let us take three elements from the set A such that x related to y and y related to z. So what we have to prove is x is related to z. So from the given conditions, 3x minus y equal to 0 and 3y minus z equal to 0. We can rewrite this as y equal to 3x and z equal to 3y. What we have to prove is x is related to z. That is, we have to prove 3x minus z equal to 0. But 3x minus z can be rewritten as 3x minus 3y, but y is equal to 3x. So this can be rewritten as 3x minus 9x, which is equal to minus 6x. But minus 6x can never be equal to 0 since x belongs to the set E. So from this, what we could conclude is x is not related to z. Therefore, the given relation R is not transitive. So for the given relation R, we have verified that it does not satisfy the three properties: reflexive, symmetric and transitive. Second one, relation R in the set n of natural numbers defined as R equal to set of all ordered pairs x, y such that y equal to x plus 5 and x strictly less than 4. Now let us write the elements present in the set R. Ordered pair 1, 6, 2, 7, 3, 8. Because x value should be strictly less than 4. So only 1, 2, 3 can be there for the first component, and y should be such that x plus 5. So 1 plus 5 is 6, 2 plus 5 is 7, 3 plus 5 is 8. Now we have to verify the three properties. Number 1, reflexive. So if you take an element from the set n, it should be related to itself. So if you take 1, it should be related to itself. 1, 1 should be there, but we don't have that. So we can say the given relation R is not reflexive. We can also prove this in the most general form by taking an element from the set n such that x is strictly less than 4. So x can be 1, 2, 3. Now we have to verify whether x is related to itself. So we have to prove that x equal to x plus 5. So if you simplify this, you will get 0 equal to 5. This statement is not true. Thus, x is not related to x. Therefore, the relation R is not reflexive. Second one, symmetric. So if you take two elements A and B such that A related to B, we have to verify whether B is related to A. So if you take A 1, 6, then we should have 6, 1. But we don't have that element. So we can conclude that R is not symmetric. We can also prove this in the general way. So let us take two elements X and Y from N such that X is related to Y and X is strictly less than 4. Now we have to verify whether Y is related to X. Since X is related to Y, what we can say is Y equal to X plus 5. Fine. So now we have to verify whether Y is related to X. So we have to prove X is equal to Y plus 5, whether this is true or not. But already we know that Y equal to X plus 5. So X equal to X plus 10. So from this what we could conclude is 0 equal to 10. This statement is not true. Therefore, X related to Y does not imply Y related to X, or simply we can say Y is not related to X. So what we could conclude is R is not symmetric. Third one, transitive. Let us take three elements x, y, z from the set of natural numbers such that x is related to y and y is related to z with the condition x is strictly less than 4. Since x is related to y, we can write y as x plus 5, and similarly y related to z can be written as z equal to y plus 5. We have to make sure whether z can be written as y plus 5. This is not possible because we have the condition that x is strictly less than 4. So in the set of ordered pairs x comma y, x should be strictly less than 4 and y should be equal to x plus 5. Then only we can consider the ordered pair x comma y in the set R. So the first component should be always strictly less than 4. But when you consider y equal to x plus 5, then we cannot consider the ordered pair y comma z, because if you write z equal to y plus 5, already y value is strictly greater than 6. So this y value can never be strictly less than 4. So such a z value does not exist. So there exists no relation from y to any other element in the set of natural numbers, right? Therefore, there exists no such pair 6 comma any natural number that belongs to the set R. Therefore, the given relation R is transitive. So you have to understand this concept clearly. We have the pair x comma y, but we don't have the pair y comma z. So obviously we no need to verify whether x is related to z. Therefore, this transitive property is satisfied. When we consider the elements in the set R, we have 1, 6, 2, 7 and 3, 8. So for the element 1, 6, we don't have any other element of the form 6, any other natural number. So we have x related to y, but we don't have y related to z. Therefore, we no need to verify whether x is related to z. So this property transitive is obviously gets satisfied. So this relation R is transitive. Third one, relation R in the set A equal to 1, 2, 3, 4, 5, 6 as R equal to set of all ordered pairs x comma y such that y is divisible by x. So only ordered pairs satisfying the condition that y is divisible by x, which means y should be a multiple of x. So y should be written as some integer, say z into x. Fine, where z can be any integer. So now let us write the elements in the set R such that y is divisible by x. So now we have to verify this relation is reflexive. So if you take an element from the set, it should be related to itself. So if I take 1, it is related to itself, 2 is related to 2, 3 related to 3, 4 related to 4, 5 related to 5 and 6 related to 6. So we can say the relation R is reflexive. We can also prove this in the general way. So let X belongs to the given set A. Now we have to verify whether X is related to itself. So we have to prove X is divisible by X. So X should be written as a multiple of X. Yes, X can be written as 1 into X, where 1 is an integer. So from this what we could conclude is X is divisible by X. Thus X is related to itself. So what we could conclude is R is reflexive. The second property, symmetric. So if you take two elements, say X and Y, from the given set A, then we have to consider such that X related to Y, then we have to verify whether Y is related to X. So if you take an element say 1 comma 2, then we have to check whether 2 comma 1 is there, but 2 comma 1 is not there in the set R. Therefore we can conclude that the relation R is not symmetric. We can prove this in the general way. So if I take two elements X and Y such that X is related to Y, this implies Y is divisible by X, that is Y can be written as a multiple of X, where Z belongs to integer. Now what we have to prove is Y is related to X, that is X should be written as a multiple of Y. So I have to write X as a multiple of Y, but from the above condition what I could say about X is equal to Y by Z. Fine, where Z is an integer. So 1 by Z will not be an integer. From this what we could conclude is X is not divisible by Y. Fine. So Y is not related to X, therefore the relation R is not symmetric. Clear? Third one, transitive. So if you take two elements such that X related to Y and Y related to Z, then we have to verify whether X is related to Z. So if you take two pairs such that 1 comma 1 and 1 comma 2, then I have to verify whether 1 comma 2 is there. Yes, 1 comma 2 is there. Similarly, if you take two elements such that 2 comma 2 and 2 comma 4, I have to verify whether 2 comma 4 is there. Yes, it is there. Fine. So from this what we could conclude is the given relation R is transitive. So let us prove that. Let X, Y, Z belongs to the set A such that X related to Y and Y related to Z. From this what we could conclude is Y can be written as a multiple of X, where Z1 is an integer, and Z can be written as a multiple of Y. Again Z2 is an integer. Now I have to verify whether X is related to Z. So Z should be written as a multiple of X. But what I know about Z is Y Z2, but Y is equal to X Z1. So X into Z1 Z2. Since Z1 and Z2 are integers, their multiple is also an integer. So Z is written as a multiple of X. So from this what we could conclude is Z is divisible by X. Fine. Therefore the relation R is transitive. Fourth one, relation R in the set Z of all integers defined as R equal to set of all ordered pairs X comma Y such that X minus Y is an integer. So now we have to verify whether the relation satisfies properties. It is not possible to write all the ordered pairs which satisfies this condition since Z is an infinite set. So let us prove this in the general way. So first we have to prove whether the relation is reflexive or not. So let us take an element from the set of integers. So let x belongs to z. Now we have to verify whether x is related to itself. That is x minus x should be an integer. We know that x minus x equal to 0. 0 is an integer, right? So if you take any element from the integer, its difference from itself will be definitely equal to 0, and that difference belongs to set of integers. So from this what we could conclude is x is related to itself. Therefore, the relation R is reflexive. The second one is symmetric. Let us take two elements from the set of integers such that x is related to y. Since x is related to y, we can say x minus y is an integer. That is x minus y belongs to the set of integers. Now what we have to prove is y minus x is also an integer. So y minus x, this can be written as minus of x minus y. We know that x minus y is an integer. So negative of an integer is also an integer. Therefore, we can say minus of x minus y is also an integer. So thus, what we have concluded is y is related to x. Therefore, R is symmetric. Third one, transitive. So if you take three elements x, y, z in the set of integers such that x is related to y and y is related to z. So from this what we could say is x minus y is an integer and y minus z is also an integer. Now what we have to prove is x is related to z, that is x minus z should be an integer. This can be rewritten as x minus y plus y minus z. We know that x minus y is an integer and y minus z is also an integer. So sum of two integers again will be an integer. So what we could conclude is this value is again an integer. Thus we have verified x minus z is an integer. So what we obtained is x is related to z. Therefore the relation R is transitive. Clear? Fifth one, a relation R in the set A of human beings in a town at a particular time given by. So number one, R equal to set of all x comma y such that x and y work at the same place. So here if you take an element x, then it will be related to itself because x and x can work at the same place, right? So 5a, the relation R is reflexive. If you take two elements x and y such that x and y work at the same place, now we have to check whether y is related to x. We can also say y and x work at the same place. Therefore, y is related to x. Therefore, the relation R is symmetric. Now, moving on to the third one, transitive. If we take three elements x, y, z such that x is related to y, that is x and y working at the same place and y and z working at the same place, then what we could say is x is related to z. From this what we could conclude is the relation R is transitive. Clear? Moving on to the relation B, R equal to set of all ordered pairs x comma y such that x and y live in the same locality. So if we take x and x live in the same locality, therefore the relation R is reflexive. If you take two elements x and y such that they live in the same locality, we can also say y and x live in the same locality. The same idea we can apply for three elements x, y, z. If x and y live in the same locality and y and z live in the same locality, we can say x and z live in the same locality. Therefore, for B, the relation R satisfies all the above properties. C, R equal to set of all ordered pairs x comma y such that x is exactly 7 centimeter taller than y. So, if you take only the element x, x cannot be related to itself because x is not exactly 7 centimeter taller than x itself. Therefore, x is not related to x. So, for the question C, the relation R is not reflexive. When you consider two elements x and y such that x is related to y, so x is exactly 7 centimeter taller than y. You cannot say y is exactly 7 centimeter taller than x because already we know x is taller than y. So you cannot say y is taller than x. So the relation R is not symmetric. In the case of transitive, if you take three elements such that x related to y and y related to z. That is, x is exactly 7 centimeter taller than y and y is exactly 7 centimeter taller than z. Is it possible for us to say x is exactly 7 centimeter taller than z? Not possible because x is 14 centimeter, exactly 14 centimeter taller than z. So, x is not related to z. Therefore, the relation R is not transitive. D. R equal to set of all ordered pairs x comma y such that x is wife of y. So if you take only one element, we cannot say x is wife of x itself. Okay. Therefore, the relation R is not reflexive. So if you take two elements x and y such that x is wife of y, you cannot say y is wife of x. Therefore, the relation R is not symmetric. If you take three elements, say x, y, z such that x is related to y, that is x is wife of y and y is wife of z, then is it possible for us to say x is wife of z? No, this relation is not possible. Therefore, the relation R is not transitive. Question number E. R equal to set of all ordered pairs x comma y such that x is father of y. Now we have to verify whether this is an equivalence relation. So if you consider the reflexive property, x should be related to itself. Is it possible to say x is a father of x itself? No. Therefore, this relation is not reflexive. Second one, symmetric. If you consider x is related to y, that is x is father of y, then you cannot say y is a father of x. That is not possible. Therefore, y is not related to x. This implies the relation R is not symmetric. When you consider three elements say x, y, z such that x is related to y and y is related to z, then we have to prove x is related to z. If x is a father of y and y is a father of z, then we cannot say x is a father of z, right? Therefore, we cannot say the relation R is transitive. So from this, what we could conclude is the given relation R is neither reflexive nor symmetric and transitive. Now moving on to the question number 2, show that the relation R in the set R of real numbers defined as R equal to set of all ordered pairs A comma B such that A is less than or equal to B square is neither reflexive nor symmetric nor transitive. So the relation is such that if you take two real numbers, then the first number should be less than or equal to square of the second number. Now we have to prove that they are not reflexive, symmetric and transitive. First property, reflexive. So if we take an element A from the set of real numbers, we have to prove that A is less than or equal to A square. This result in general is not true because when you take an element, say A equal to 1 by 2, then 1 by 2 less than or equal to its square, that is 1 by 4, is not true. But if you take A equal to say 1 or 2, this result will be true. So, for certain real values, this result is not true. Therefore, A is not related to A for all the real numbers. Therefore, the relation R is not reflexive. Moving on to the second one, symmetric. If we take two elements, say A and B, from the set of real numbers such that A is related to B, which means A is less than or equal to B square. Now we have to prove that B is less than or equal to A square. This result is also not true for certain real numbers. For example, let us take two real numbers, say 2 and 5. 2 will be less than or equal to 5 square, that is 25. If we consider B less than or equal to A square, then 5 must be less than or equal to A square, that is 4. But 5 less than or equal to 4 is not true. Thus, A related to B does not imply B related to A in this case. So, in general, what we could conclude is this relation R is not symmetric. Moving on to the third property, transitive. Here, we need to take three elements A, B, C from the set of real numbers such that A is related to B and B is related to C. So this implies A is less than or equal to B square and B is less than or equal to C square. Now we have to prove A is related to C, that is A is less than or equal to C square. Let us consider an example such that A equal to 5, B equal to 3 and C equal to 2. 5 is less than or equal to 3 square, that is 9, and 3 is less than or equal to 2 square, 4. Thus A is related to B and B is related to C. Whether these two conditions imply 5 is less than or equal to 4, that is A is related to C? No, this is not true. Therefore, the relation R is not transitive. Thus, we have verified the problem number 2, that the relation R is not reflexive, symmetric and transitive. Problem number 3, check whether the relation R defined in the set 1, 2, 3, 4, 5, 6 as R equal to set of all ordered pairs A, B such that B equal to A plus 1 is reflexive, symmetric or transitive. So the set consists of natural numbers from 1 to 6 and the relation is such that the second element in the ordered pair is equal to A plus 1, that is the first element plus 1. So now let us identify the elements in the relation. Now let us verify all the three properties. First one, reflexive. So if you take an element from the set A, it should be related to itself. So if you take 1, 1 should be related to 1. So 1 comma 1 should be there. But in this set R, we don't have any element like 1 comma 1 or 2 comma 2, 3 comma 3, etc. Therefore, this relation R is not reflexive. We can also prove this such that if you take an element A from the set capital A, then what we have to prove is A equal to A plus 1. This implies 0 equal to 1, which is not true. Therefore, the set R is not reflexive. Moving on to the second property, symmetric. So in the set itself you can verify. If you take 1 comma 2, 2 comma 1 should be there. Here it is not there, therefore it is not symmetric. We can also prove this by taking two elements in the set such that A is related to B. So this implies B equal to A plus 1. What we have to prove now is B is related to A, that is A equal to B plus 1. Clear? But what we know about B is B equal to A plus 1. So A plus 2. So this implies 0 equal to 2. This is not true. Therefore, B is not related to A. This implies this. The relation R is not symmetric. And the third one is transitive. In the set, if you take two elements such that 1, 2 and 2, 3, we don't have 1, 3. Therefore, this is not transitive. So, let's take 3 elements from the set such that A related to B and B related to C. So, this implies B equal to A plus 1 and C equal to B plus 1. Now, what we have to prove is C equal to A plus 1, that is C is related to A. So, if we consider C equal to A plus 1, then A plus 1 can be written as B, but B can be again rewritten as C minus 1. So, from this what we could conclude is 0 equal to minus 1, which is not true. Therefore, A is not related to C. Thus, the relation R is not transitive. So, thus we have verified that the given relation is neither reflexive nor symmetric nor transitive. Problem number 4. Show that the relation R in set of real numbers defined as R equal to set of all ordered pair A, B such that A less than or equal to B is reflexive and transitive but not symmetric. So, let us first verify the reflexive property. So, if you take a real number, we have to check whether A is less than or equal to A. So, A less than or equal to A is true for all real numbers. Therefore, R is reflexive. The second one is symmetric. So, if you take two real numbers such that A is related to B, which implies A is less than or equal to B. Now, what we have to verify is B is less than or equal to A. Clear? This is true only when A and B are equal. In other case, it is not necessarily should be true. For example, if you take two real numbers, say 1 and 2, 1 is less than or equal to 2 is true, but 2 less than or equal to 1 is not true. Therefore, the relation R is not symmetric. Third one is transitive. So, if you take 3 elements from the set R such that A is related to B and B is related to C. So, we know that A is less than or equal to B and B is less than or equal to C. Now, what we have to prove is A is less than or equal to C. What we know is A is less than or equal to B, but B is less than or equal to C. So, from this what we could conclude is A is less than or equal to C, thus A is related to C. Therefore, the relation R is transitive. So, thus we have verified that the given relation R for the set of real numbers is reflexive and transitive but not symmetric. Problem number 5. Check whether the relation R in set of real numbers defined by R equal to set of all ordered pairs A, B such that A less than or equal to B cube is reflexive, symmetric or transitive. So, let us now consider the first one, reflexive. So, if you take any real number, say A, we have to verify whether A is less than or equal to A cube. This is not true. For example, if you take A to be 1 by 2, then 1 by 2 is less than or equal to its cube, that is 1 by 8, is not true. Therefore, A is not related to A. Thus, the relation R is not reflexive. The second one is symmetric. So, let us take two real numbers such that A is related to B. That is, A is less than or equal to B cube. Now what we have to verify is B is less than or equal to A cube. But this result is not true. For example, if you take two real numbers, say 2, 10, then 2 is less than or equal to 10 cube, that is 1000. But 10 less than or equal to 2 cube, that is 8, is not true. Thus, A related to B does not imply B related to A. Therefore, the relation R is not symmetric. The last one, transitive. To prove a result to be true, it is necessary to verify whether it is true for all the elements in the set. But if you want to prove it to be not true, then it is enough to give a counter example. So if you take three elements, say A, B, C, from the set of real numbers such that A is related to B and B is related to C. Now we have to verify whether A is related to C. So this implies A is less than or equal to B cube and B is less than or equal to C cube. From this we have to prove A is less than or equal to C cube. Right? This is not true in general. For example, if we take three numbers, say 10, 3, 2, then 10 less than or equal to 3 cube 27 is true, and 3 less than or equal to 2 cube 8 is also true, but 10 less than or equal to 2 cube 8 is not true. Thus, the relation R is not transitive. So, for the set of real numbers with the given relation, we have verified that the relation is neither reflexive nor symmetric nor transitive. Problem number 6. Show that the relation R in the set 1, 2, 3 given by R equal to set of all ordered pairs 1, 2 and 2, 1 is symmetric but neither reflexive nor transitive. So the set consists of only 3 elements and the relation elements they have given 1, 2 and 2, 1. First let us verify whether it is reflexive. If you take any element from the set, it should be related to itself. So we should have 1, 1, 2, 2 and 3, 3 in the set R. But we don't have that. In general, we don't have any element of the form x, x in the set R. Therefore, the relation R is not reflexive. For the second one, symmetric property, we have to prove that x related to y implies y related to x. So, we have the element 1, 2 in the set R and we should have 2, 1. We have that. Therefore, this relation R is symmetric. In the case of transitive, in the set R, we have 1, 2 and 2, 1. So, we should have 1, 1. But we don't have that element. Therefore, this relation R is not transitive. Thus, we have verified that the given relation R is symmetric but neither reflexive nor transitive. Problem number 7. Show that the relation R in the set A of all the books in the library of a college given by R equal to set of all ordered pairs x, y such that x and y have same number of pages is an equivalence relation. So the set what we have to consider is consisting of all the books in the library of a college and the relation is defined such that for every ordered pair x, y, x and y will denote the books in the library and they should have same number of pages. Then only we can say x and y are related. And we have to prove that R is an equivalence relation. Let us verify the first property, reflexive. So if you take an element X from the set A such that X is a book in the library, then X will have same number of pages as that of X itself. Therefore, what we could conclude is X is related to X itself. Therefore, the relation R is reflexive. The second one is symmetric. If you take two books in the library such that X will have same number of pages as that of Y, then we can also say Y will have same number of pages as that of X. So Y is related to X. So thus we have verified the relation R is symmetric. Third one is transitive. Here we have to consider three elements from the set A. Let X, Y, Z belongs to the set A such that X is related to Y and Y is related to Z. That is, X and Y will have same number of pages and Y and Z will have same number of pages. From this, we could conclude that X and Z will have same number of pages. So, we can say that X is related to Z. Therefore, R is transitive. Since the relation R is reflexive, symmetric and transitive, we can conclude that the relation R is an equivalence relation. Problem number 8. Show that the relation R in the set A equal to 1, 2, 3, 4, 5 given by R equal to set of all ordered pairs A, B such that absolute value of A minus B is even is an equivalence relation. Show that all the elements of 1, 3, 5 are related to each other and all the elements of the set 2, 4 are related to each other, but no element of the set 1, 3, 5 is related to any element of 2, 4. Our set A consists of 5 elements and the relation what they have defined is the absolute value of the difference between the two elements will be an even number, and we have to prove that this is an equivalence relation. Also, we have to show that the elements of the subset 1, 3, 5 are related to each other, and similarly the elements of the subset 2, 4 are related to each other, and we cannot find relation between the elements of these two subsets. Now let us prove this. Absolute value of x minus x equal to 0 is an even number. So this implies x is related to x. Therefore, the relation R is reflexive. And second one, symmetric. If you consider two elements such that x is related to y, which implies the absolute value of the difference between x and y is an even number. Okay, so this is equal to an even number. Then we have to prove the absolute value of the difference y minus x is equal to an even number, but this can be rewritten as minus x minus y. So again we can rewrite this like this. So this is equal to an even number, right? Thus we have verified x related to y implies y related to x. Therefore the relation R is symmetric. Third one is transitive. So if you consider three elements x, y and z such that x is related to y and y is related to z with the conditions that x minus y is an even number and y minus z is also an even number, then we have to check whether x minus z is an even number. Since the difference between x and y is an even number, x and y should be either both even or both odd numbers. Then only we can have the difference to be an even number. So this implies either x and y should be even number or x and y should be odd number. So in both the cases we will have the difference to be even number. So this implies that x and z should be both even number or odd number. So this implies their difference, absolute value of their difference again will be an even number. So from this we have verified that x is related to z. Thus the relation R is transitive. So we have proved that the relation R is an equivalence relation. Also we have to verify that the subsets 1, 3, 5 and 2, 4 satisfies the conditions given in the question. If you consider the subset 1, 3, 5, we have to verify whether the elements are related to themselves. So if you take 1 and 3, their difference is 2, and for 3 and 5, again it is 2, an even number. For 5 and 1, again it is an even number. So all the elements in this subset are related to themselves. For the subset 2, 4, if you find the difference, it is an even number. Thus, we have verified the conditions given in the question. We can also verify whether the elements of the subset 1, 3, 5 and the elements of the subset 2, 4 are related or not. If you take one element from this subset say 1 and one element from the other subset say 2, and if you find the difference you will get the value to be 1, which is not an even number. Similarly, if you take any element from this subset and if you find the difference between the elements of the other subset, you will get only odd values. Therefore, the elements in this subset are not related to the elements in the other subset. Problem number 9. Show that each of the relation R in the set A equal to set of all x belongs to set of integers such that x lies between 0 and 12, given by, they have given two relations R equal to set of all ordered pairs A comma B such that the absolute value of the difference A minus B is a multiple of 4, and the second one is R equal to set of all ordered pair A comma B such that A equal to B is an equivalence relation. Find the set of all elements related to 1 in each case. So now let us consider the first relation. Let us verify the first property, reflexive. So if I take an element from the set X, then it will lie between 0 and 12. And now I have to verify whether the absolute value of A minus A is a multiple of 4. But A minus A equal to 0, which is a multiple of 4. So we can say that A is related to A. Fine. So the relation R is reflexive. The next property is symmetric. If you take two elements A and B from the set A such that A is related to B, which implies the absolute value of the difference A minus B is a multiple of 4, that is 4 into some integer say Z. Then we have to prove B is related to A, that is the absolute value of the difference B minus A is equal to some multiple of 4, right? But this can be rewritten as minus A minus B. This is equal to A minus B. So again we have proved that this is a multiple of 4. Thus we have proved that B is related to A. So this implies the relation R is symmetric. The last one is transitive. For this we have to consider three elements x, y, z such that x is related to y and y is related to z. So this implies difference between x and y is a multiple of 4, and the difference between y and z is also a multiple of 4, z1. Now we have to verify whether the absolute value of the difference x minus z is a multiple of 4. Since their difference should be multiple of 4, x and y both are either odd or even numbers. So this implies x and y should be both either odd numbers or even numbers. So this implies the absolute value of the difference x and z will be equal to a multiple of 4. Right? So thus we have verified x is related to z. Therefore the relation R is transitive, and we have verified that the relation R is an equivalence relation. The second relation given is R equal to set of all ordered pairs A comma B such that A equal to B. So let us verify the first property. So if you take an element say A from the set A, then A is equal to A implies A is related to A. Therefore, the given relation is reflexive. The second one is symmetric. So if you take two elements A and B such that A is related to B, so this implies A equal to B. Now we have to verify whether B is related to A. Since A equal to B, we can say B equal to A. So this implies B is related to A. Therefore, the relation is symmetric. Third one is transitive. For this, let us take three elements A, B, C such that A is related to B and B is related to C. So this implies A equal to B and B equal to C. So we can say A equal to B equal to C implies A equal to C. Therefore, A is related to C. Thus, we have verified the relation is transitive. So we can conclude that the given relation R is an equivalence relation. Also, we have to find the set of all elements related to 1 in each case. So in both the cases, we have to identify the elements in the set A which are related to 1, such that for the first relation, we have to identify the numbers in the set A such that the difference between that number and 1 should be a multiple of 4. Before discussing that, we can also determine the elements in the relation for both the cases. For the first one, the elements in the set R will be, for the second case, the set R equal to. So now for the first relation, the set of elements that are related to 1 will be 1, 5, 9, because only for these elements their absolute difference will be equal to multiple of 4. For the second case, 1 is equal to 1. So only the element 1 is related to itself. So thus we have determined the elements in both the relations that are related to 1. Problem number 10. Give an example of a relation which is, they have given 5 different cases. So we have to give example for all these cases. Number 1, symmetric but neither reflexive nor transitive. Let us take a very simple example. If you take any element from the set A, the element is not related to itself. That is, we don't have any element of the form x comma x in R. Therefore, the relation R is not reflexive. In the case of symmetric, if you consider 1 comma 2, we have 2 comma 1. Therefore, x related to y implies y related to x. Thus, the relation R is symmetric. When you consider 1 comma 2 and 2 comma 1, for transitive we should have 1 comma 1, but we don't have that element. Therefore, x related to y and y related to z does not imply x related to Z. Thus, this relation is symmetric but not reflexive and transitive. We can also give one more example which we have already discussed, that set of straight lines where the relation is the two lines L1 and L2 are related only if L1 is perpendicular to L2. So here if you take two lines, they are perpendicular to each other. So x related y will implies y related to x, but a line is not perpendicular to itself, therefore it is not reflexive. If you take three lines L1, L2, L3, L1 is perpendicular to L2 and L2 is perpendicular to L3, but L1 and L3 will not be perpendicular to each other. Therefore, this is an example of a relation which is symmetric but neither reflexive nor transitive. Second one, transitive but neither reflexive nor symmetric. Here we don't have any element which is related to itself, that is 1, 1, 2, 2, 3, 3 is not there. Therefore, x is not related to itself. Thus, this relation R is not reflexive. When you take two elements, say 1, 2, such that x is related to y, then we have to prove y is related to x, but we don't have 2, 1. Therefore, x related to y does not imply y related to x. Therefore, this relation R is not symmetric. When you consider three elements 1, 2, 3, in our relation we have 1, 2, 2, 3 and we have 1, 3 also. So, x related to y and y related to z implies x related to z. Therefore, this relation is transitive. We can also consider one more example, the set to be set of all real numbers, where the relation R is consisting of ordered pairs x, y such that x is strictly less than y. So, if you take an element x, then we cannot say x is strictly less than x. Therefore, this is not reflexive, and if you take x less than y, we cannot say this implies y is less than x. So, this is also not possible. Therefore, this relation is not symmetric. But when you consider three elements x, y, z such that x is less than y and y is less than z, then we can say x is less than z. Thus, the relation what we have considered is transitive. So, we have given example for a relation which is neither reflexive nor symmetric, but it is transitive. Third one, reflexive and symmetric but not transitive. So, now let us verify whether this is reflexive. So, if you take any real number, their absolute difference between x and x will be equal to 0. So, the absolute value is less than or equal to 1. Thus, it is reflexive. If you take two numbers x and y such that x is related to y, this implies modulus of x minus y is less than or equal to 1. So, now we have to verify whether y is related to x. In order to prove that, we have to verify whether modulus of y minus x is less than or equal to 1. So, modulus of y minus x can also be written as minus x minus y. So, this is nothing but modulus of x minus y. Again, this will be less than or equal to 1. In the case of transitive, if you take three elements such that x is related to y and y is related to z, we have modulus of x minus y is less than or equal to 1 and modulus of y minus z is less than or equal to 1. Now we have to check whether x is related to z, that is modulus of x minus z is less than or equal to 1. So, this is equal to x minus y plus y minus z. So, by the inequality, we can rewrite this as modulus of x minus y plus modulus of y minus z. But we know that this modulus value is less than or equal to 1 and this is also less than or equal to 1. So, 1 plus 1 equal to 2. So, what we have obtained is modulus of x minus z is less than or equal to 2. Thus, x is not related to z. So, the relation what we have considered is reflexive and symmetric but not transitive. Fourth one, reflexive and transitive but not symmetric. If you consider a set A with 3 elements, 1, 2, 3, then each element is related to itself. Since we have 1, 1, 2, 2, 3, 3, we can say x is related to x itself. Therefore, the relation R is reflexive. When you consider an element say 1, 2 from the set R, then we should have 2, 1. Similarly, for 1, 3, we should have 3, 1. But we don't have 2, 1 and 3, 1. Therefore, the given relation R is not symmetric. So when you consider 1, 1, 3, then we should have 1, 3, we have that. And if you consider the elements 2, 2 and 2, 3, then we should have 2, 3, we have that. Therefore, for x related to y and y related to z, we have x related to z. Therefore, the given relation R is transitive. We can also consider one more example by considering the set to be set of all real numbers, and the relation is defined such that A is related to B only if A is less than or equal to B. So if you consider an element A from the set of real numbers, then we can say A is related to A since A is less than or equal to A. Therefore, the relation R is reflexive. But if you consider two elements such that A is less than or equal to B, we cannot say B is less than or equal to A. Therefore, A related to B does not imply B related to A. Therefore, the relation R is not symmetric. When you consider three real numbers such that A less than or equal to B and B less than or equal to C, we can say A is less than or equal to C. Therefore, the relation R is transitive. Thus, this is an example for a relation which is reflexive and transitive but not symmetric. Fifth one, symmetric and transitive but not reflexive. In this relation, we don't have elements such as 3, 3, 1, 1. Therefore, this relation is said to be not reflexive. When you consider the element 2, 4, we have 4, 2. So, from this we can say the relation R is symmetric. Similarly, if you consider the elements 2, 2 and 2, 4, we have 2, 4. Therefore, the given relation R is said to be transitive. Thus, this is an example for a relation which is not reflexive but symmetric and transitive. Question number 11. Show that the relation R in the set A of points in a plane given by R equal to set of all ordered pairs P, Q such that distance of the point P from the origin is same as the distance of the point Q from the origin is an equivalence relation. Further, show that the set of all points related to a point P not equal to 0, 0 is the circle passing through P with origin as center. So, let O denotes the origin. First, let us verify reflexive property. So, if we consider a point P in our set A, so that its distance from origin be OP. Since the distance of the point P from the origin is always same as that of the distance of the same point from the origin, we can say OP equal to OP. Therefore, we can say P is related to the same point P, which implies R is reflexive. Second one, symmetric. Let us take 2 points P and Q in our set A such that P is related to Q. This implies the distance of the point P from the origin, that is OP, is equal to the distance of the point Q from the origin, that is OQ. We can also write OQ equal to OP. So this implies the distance of the point Q from the origin is equal to distance of the point P from the origin. Therefore, Q is also related to P. From this, we can say R is symmetric. Third one, transitive. Let us take 3 points P, Q, R, the given set A, such that P is related to Q and Q is related to another point, say S. So from this what we could conclude is OP equal to OQ and OQ equal to OS. What we need to prove is P is related to, yes, this is what we have to prove. So we want to prove OP equal to OS. Since OP equal to OQ and OQ equal to OS, we can write OP equal to OS. So this implies P is related to the point S. So that the distance of the point P from the origin is same as that of the distance of the point S from the origin. Therefore, the relation R is transitive. Since the three properties got satisfied, what we could conclude is R is an equivalence relation. And it is to be noted that set of all points that are related to P will have same distance from the origin O, so that they will definitely form a circle which passes through the point P and having the center to be the origin. Problem number 12. Show that the relation R defined in the set A of all triangles as R equal to set of all ordered pairs T1, T2 such that T1 is similar to T2 is equivalence relation. Consider three right angle triangles T1 with sides 3, 4, 5, T2 with sides 5, 12, 13 and T3 with sides 6, 8, 10. Which triangles among T1, T2 and T3 are related? Here they have given that the set A consists of all triangles and the relation R is defined such that T1 is related to T2 if T1 is similar to T2. Two triangles are said to be similar if their corresponding angles are congruent and their corresponding sides are in proportion. That is, they will be in same shape but not necessarily of same size. Now we have to prove this relation R is an equivalence relation. Also they have given three right angled triangles T1, T2 and T3 with their sides, and we have to identify which among these three triangles are related. So first let us verify whether the relation is equivalence. Number 1, reflexive. So if you take a triangle T1 from the set A, then T1 will have same size as well as same angle as that of T1 itself. Therefore, we can say T1 is similar to T1. So, from this what we could conclude is T1 is related to T1 itself. Therefore, the relation R is reflexive. Second one, symmetric. If you take two triangles, say T1 and T2 from the given set A, such that T1 is related to T2, that is T1 is similar to T2. T1 and T2 will have same angles but their sides will be in proportion. So this implies T2 is also similar to T1. So T2 is related to T1. So this gives R is symmetric. Third one, transitive. So let us take three triangles T1, T2 and T3 from the given set A such that T1 is related to T2 and T2 is related to T3. So T1 is similar to T2 implies the corresponding angles are congruent and their sides are in proportion. Also T2 is similar to T3, therefore their corresponding angles are congruent and their corresponding sides are in proportion. So from this what we could conclude is T1 is similar to T3 since their corresponding angles will be congruent and their corresponding sides will be in proportion. So this implies T1 is related to T3. Therefore the relation R is transitive. Since the three properties got satisfied, we can conclude that R is an equivalence relation. Further, we have to identify which among these three triangles are related. It is to be noted that all these three triangles are right angular triangles. Their corresponding sides should be proportional. If we take the ratio between T1 and T2, then we will get 3 by 5 equal to 4 by 12 equal to 5 by 13. If we verify this, this is not true. Therefore, T1 is not related to T2. If we take T2 and T3, then the ratio between their corresponding sides will be 5 by 6, 12 by 8 equal to 13 by 10. We have to verify whether this is true. This is not true. Therefore, T2 is not related to T3. The last one, T1 and T3. So if we find the ratio between their corresponding sides, we will get 3 by 6 equal to 4 by 8 equal to 5 by 10. So if we simplify this, all these ratios are equal to 1 by 2. Therefore, their corresponding sides are in proportion. So this implies T1 is related to T3. So among the three right angular triangles, T1 and T3 are related under the relation is similar to given in our question. Question number 13. Show that the relation R defined in the set A of all polygons as R equal to set of all ordered pairs P1, P2 such that P1 and P2 have same number of sides is an equivalence relation. What is the set of all elements in A related to the right angle triangle T with sides 3, 4, 5? So the relation R is defined such that P1 is related to P2 only when P1 and P2 have same number of sides. Since it's a polygon, it may have any number of sides, right? So only when both the polygons have same number of sides, then they are said to be related. So let us verify the first property, reflexive. So if you consider a polygon, say P1 from the given set A, then it will have same number of sides as that of P1 itself. So from this we can conclude P1 is related to P1. Therefore, the relation R is reflexive. Second one, symmetric. So let us take two polygons from the set A, say P1 and P2, such that P1 is related to P2, which means P1 and P2 will have same number of sides. From this we can say P2 has same number of sides as that of P1. Therefore, P2 is related to P1. From this we can conclude that the relation R is symmetric. Moving on to the third property, transitive. Let us consider three polygons, say P1, P2 and P3 from the given set A such that P1 is related to P2, P2 is related to P3. So this implies P1 and P2 will have same number of sides and P2 and P3 will have same number of sides. So from this we can say P1 and P3 will have same number of sides. Therefore P1 is related to P3. So the relation R is transitive. Since the three properties got satisfied, the relation R is an equivalence relation. Also, we have to identify the set of all elements in the given set A that are related to the right angle triangle T, which is of sides 3, 4 and 5. Since the relation given to us is that two polygons should be of same number of sides, and the polygon given to us is a triangle. In fact, it is a right angle triangle with sides 3, 4, 5. So the new set of elements that we are going to form, say A dash, will consist of all triangles. Not necessarily they should be right angle triangles, because the relation is given such that the number of sides of the polygon should be same. So all the triangles will have 3 sides. Question number 14. Let L be the set of all lines in xy plane and R be the relation in L defined as R equal to set of all ordered pairs L1, L2 such that L1 is parallel to L2. Show that R is an equivalence relation. Find the set of all lines related to the line y equal to 2x plus 4. So first let us verify reflexive. The relation R is defined such that if the line L1 is parallel to L2, then we can say L1 is related to L2. So let us consider a line L1 from the given set A. It is to be noted that every line is parallel to itself. So L1 is related to L1. Therefore, the relation R is reflexive. Second one, symmetric. If you take two lines L1 and L2 from the set of straight lines in the xy plane such that L1 is parallel to L2. We can also say L2 is parallel to L1. So this implies L2 is related to L1. Therefore, the relation R is symmetric. The third one is transitive. So let us take three lines L1, L2 and L3 such that L1 is related to L2 and L2 is related to L3. Since L1 and L2 are related, L1 is parallel to L2 and L2 is parallel to L3. So this implies L1 is parallel to L3. So this implies L1 is related to L3. Therefore, the relation R is transitive. Since the three properties got satisfied, we can say the relation R is an equivalence relation. Now we have to identify the set of all lines that are related to the line y equal to 2x plus 4. From the given straight line, we can observe that here the slope m is equal to 2 and the y-intercept c is 4. We have to identify the lines in the set A that are parallel to this line y equal to mx plus 4. Since the two lines should be parallel, they should have same slope. So our set A dash consists of lines in the given set A such that its slope will be same as that of the line y equal to 2x, but its y-intercept can be any real number. So it consists of straight lines which are of the form y equal to 2x plus k, where k is any real number. Problem number 15. Let R be the relation in the set 1, 2, 3, 4 given by R equal to set of all ordered pairs 1, 2, 2, 2, 1, 1, 4, 4, 1, 3, 3, 3, 3, 2. So they have given the set which consists of elements 1, 2, 3, 4 and they have given the relation in the roster form. We have to choose the correct answer. So for the given set and the given relation, we have to verify all the three properties and from that we can choose the correct one. Now we have to verify whether it is reflexive, symmetric and transitive. So first one is reflexive. We have to verify that each and every element in the set A is related to itself. So if you take 1, it should be related to itself. So 1 comma 1 should be there. It is there. 2 comma 2 is also there. 3 comma 3 is also there. 4 comma 4 is also there. Therefore, each and every element, say A, in the given set A is related to itself. That is, A is related to itself. Therefore, the given relation R is reflexive. Next one is symmetric. Since we have 1 comma 2 but 2 comma 1 is not there, we can say the given relation R is not symmetric. Third one, transitive. So if you take three elements, say A, B, C, such that A related to B, B related to C, then A should be related to C. So if we consider an element, say 1 comma 3 and 3 comma 2, we should have 1 comma 2. We have 1 comma 2. Similarly, if we consider 1 comma 1, 1 comma 2, we should have 1 comma 2. We have that. So if you take any two elements such that A related to B and B related to C, you will definitely get A related to C. So from this, what we could conclude is the relation R is transitive. From this, what we could conclude is the relation R is reflexive and transitive but not symmetric. Therefore, option B is the correct answer. Problem number 16. Let R be the relation in the set N given by R equal to set of all ordered pairs A comma B such that A equal to B minus 2 for B greater than 6. Choose the correct answer. So from the condition B should be strictly greater than 6, option A is not possible. So only we have to verify B, C and D. Since A equal to B minus 2, only option C satisfies that condition. Therefore, option C is the correct answer. So with this, we have completed exercise 1.1 and in the next video, we will discuss the section 1.3 types of functions. If you have any doubt, please comment in the comment section. If you like the video, click the like button and share the video to your friends. Please subscribe to the channel. Thank you.